So, to help us understand the thermodynamic relation, there is something called Maxwell relation, which is very famous in thermodynamics, and typically people try to remember it, but I will show you a way that you do not have to remember at all. You have to just remember one thing, that all thermodynamic potentials are exact differential, and i.e. they are state functions. Just like u is a state function, a is a state function, g is a state function, h is a state function. So, they are all state functions, and therefore, they are all exact differential. What it means is that, as I told you, that exact differential, for example, I gave you the definition of exact or example of exact differential as height of the ground. So, whether you go along x and then along y, or go along y and then along x, height does not matter. Height of a particular point is just the characteristic of that point itself. It does not matter how you go to that particular point. You can make 5 rounds and then go to the point, your still height will be the same. So, height is, you can say, an exact differential when you talk about the ground. Similarly, a, which depends on NVT, or rather just I will just write Vt, because we are not talking about n here, we are talking about one component system. So, I will just say a as a function of V and T. Now, it is a function of multidimensional variables, and a is known to be or it is an exact differential. So, since it is an exact differential, it does not matter whether we change the V and then change the T, or change the T and then change the V, the value will remain the same, and that can be exploited in order to obtain different Maxwell relations. So, I will show you how. So, for example, if I do d2a by dv dt, which means that I am talking about, or let us say let us make it a little bit more simple. So, let us say if I take a derivative of v first at a constant t, and then this quantity I take the derivative of that again with respect to t at a constant v. It is the same as if I take the derivative with respect to t first at a constant v, and then this quantity I take the derivative with respect to v at a constant t. So, they are same, and they are same because it is an exact differential. So, you see that by exploiting the properties of exact differential, we can get now many more relations. For example, we know that dA by dV at a constant t is what? So, we have discussed that here. dA by dV at a constant t is nothing but minus p. So, this is nothing but minus p. So, we write del t of minus p at a constant v is del v of, what is dA by dt at a constant v? dA by dt at a constant v, I will show you, is minus s. Minus s at a constant t. So, minus del p del t at a constant v is minus del s del v at a constant t, and minus minus cancels. So, we get del p del t at a constant v is del s del v at a constant t, and that is so much more helpful. We can easily design an experiment where the volume is fixed, we change the temperature and measure the pressure, and that is somehow, if we did an isothermal experiment where we change the volume and measure the entropy. First of all, measuring the entropy is very difficult, and but we are getting the same information that if we, let us say, for example, if I talk about an isothermal expansion. So, we know that in isothermal expansion entropy increases, right. So, we do an isothermal expansion and we cannot calculate the entropy, right, but the entropy change that will happen in that isothermal expansion is same as if we did the same experiment by fixing the volume and change the temperature and calculate the pressure. So, that means, if you fix the volume, increase the temperature, pressure is going to change, and that is somehow reflective of the change in entropy with expansion volume. Without doing this derivation, it is impossible to even physically understand why that would be the case. So, this is one of the Maxwell relation that we get. So, this is one Maxwell relation. Similarly, we can exploit free energy, Gibbs free energy in order to do that, and we know that Gibbs free energy G depends on two quantity. So, and G depends on P and T, right. So, G is a function of P and T. So, we can write del G by del T at a constant P, and the same thing we now take a derivative with respect to T at a constant P at a constant T. So, this will be same as if I take the derivative with respect to P first at a constant T, and then take the derivative with respect to T at a constant P. Now, we have to just put the values of what is del G by del T at a constant P. So, for that I will just remind you that the dG is V dP minus S dt. I will just check once. Yes, here it is. Again, you do not have to remember, you can derive again from directly from u, and then do the Legendre transformation of both the variables, make it Pt, you get h minus Ts, take the derivative dg equal to dh minus Tds minus S dt, and you will arrive at Vtp. It will take time, but you do not need to memorize it, you can actually derive it. Now, you know that del G by del T at a constant P. So, when you say constant P, this quantity goes to 0, del G by del T will give you minus S. So, del P del T of minus S at a constant T is nothing but, and what is dG by dP at a constant T? That is nothing but V. So, del D del T of a V at a constant P. So, what we get now? Minus del S by del P at a constant T is nothing but del V del T at a constant P. And how remarkable is that? We can maintain the pressure, atmospheric pressure, change the temperature, and calculate the volume. That is somehow calculating the change in entropy by changing the pressure. So, Maxwell relations make it possible to obtain this kind of relations. So, as you can see, we have got two relations with two thermodynamic potentials A and G. Similarly, we can use H and U to get two more thermodynamic relations, and there are 4 such thermodynamic relations, but without calculating that, we can introduce a mnemonic and help you remember this particular thing. So, the mnemonic that is typically used, and why we are using mnemonic, not to memorize, but to just we can derive everything again. We can use U as let us say U, we know that as U is a function of S and V. So, our formula for U will be del 2 U as a function of del S del V. So, we are writing in a short notations that first we take derivative with respect to V at a constant S, and then with respect to S at a constant V is same as del 2 U as del V del S. If you use this relation, you get another Maxwell relation, and for H is a function of P and S. So, this will give you another Maxwell relation. But instead of remembering that, instead of deriving that, we can also remember it. There is a pretty easy way to remember it, that is called mnemonic. And in that mnemonic, you have to remember this thing. You can say this. I do not know any, in the want of any better mnemonic, I can write this: sun, please turn violet. Okay, you can find some mnemonic for S, P, T, V. So, what I want to mean is that S, P, T and V, that you have to put it in this order, or you can write another mnemonic. Some people are truly What is with V? Beautiful. Anyway, so you can decide. The point is that you have to remember SPTV. Okay. So, you have so basically you have to write S, P, T and V in this order, and then you can do this derivative like this. If you do that del P del S at a constant V, the arrow comes just like this, and that will correspond to del T del V at a constant S. Okay. So, we will write that here, del P del S at a constant V is del T del V at a constant S. However, as you can see, one arrow is going down and another arrow is going up. So, therefore, there is a negative sign. You can put the negative sign for either of them, but for going down you can put a negative and going up you can put a positive one. So, you get one Maxwell relation like this. The reason that you have to write SPTV is because if you write SPTV, your internal energy S depends on S and V, your enthalpy depends on S and P, your Gibbs free energy depends on P and T, and your Helmholtz free energy depends on A and T. So, that is the reason you need to write this SPTV, because these are the thermodynamic potentials that are governing this 4. So, that is the reason SPTV are required, and that is the reason you are getting this. So, whenever you are getting a relation between this S and V, so that is coming from U. I showed you the relation between for A and G, right. So, let us do that. So, for that we need V and T. So, in order to do that again, we can write S P T V, and we want to do V and T. So, V and if we want to do with respect to V and T, so we can go this way, del P del T at a constant V will be same as del S del V at a constant T, and in both cases they are coming down. So, both are negative. So, how do I write that? I write del P del T at a constant V, coming down means negative, let us say, is same as del S del V at a constant T, that is also negative, and negative negative cancels each other. So, we get del P del T at a constant V is equal to del S del V at a constant T. So, you see how I got that from this particular arrow, I got that. So, del P, I took del P del T at a constant V. So, arrow goes this way. Now, I have to do the parallel arrow. So, P parallel is S. So, del S del V going this way, and both are going downwards. So, therefore, the arrows are downwards and both are negative. So, I put the negative sign, and this is obtained exactly obtained above, as you can see when we derived the Maxwell relations from A. You see, this is the relation that we got, del P del T at a constant V is del S del V at a constant T. So, this is from A. Now, similarly from G we can get that, and from H also we can get that. So, we will get all of them. So, let us do another one. So, for another one we want to do with respect to, H depends on S and P, right. So, we want to do on S and P. So, we can do del T del P at a constant S, which in that case the arrow goes this way. So, therefore, the alternate arrow will go this way. So, that will be equal to del V del S at a constant P, and now both the arrows are going above. So, both are positive. Now, one more is remaining. So, this is from H and one more remaining is P and T. We want P and T. So, del S by del P at a constant T, we want to do that. So, del S by del P at a constant T is equal to, then use a different color, del V by del T at a constant P. Now, you can see that one is coming down, another is going up. So, del S by del T, del S by del P at a constant T will be a negative 1. So, this is again obtained from G. So, these are the four Maxwell relations that you got, and they are all obtained because of the fact that thermodynamic potentials are exact differentials, and we just use their intrinsic variables to obtain this particular quantity. Remember, the most important thing is that they are used to make our life simpler. So, that experiments can be done on something which is measurable and simple, and then can be related to something which cannot be measurable or very difficult to measure. So, there are some experimentally measurable quantities, they are like easily experimentally measurable quantities, such as del V by del T at a constant P. So, as I said like earlier also, for example, this is difficult to measure, but let us say this is easy to measure. So, the thing is that there are some quantities which are easy to measure, and they are in general called compressibility factors. And they are second derivative of fundamental equation. For example, these are the three quantities. One is coefficient of thermal expansion known as alpha, which is defined to be 1 by V del V by del T at a constant P. Second one is isothermal compressibility, which is called kappa T, which is minus 1 by V del V by del P at a constant T. You see, isothermal compressibility means temperature has to be fixed. Compressibility means what? Volume decreases, and therefore, there is a minus sign is there, because when you increase the pressure, when P is positive, V will be negative, and by putting a negative term we get a positive value of compressibility, and 1 by V is just to normalize it. Similarly, coefficient of thermal expansion says that if you put the temperature, then the volume will expand. 1 by V is again to normalize it, and in that case the pressure is kept constant. And heat capacity. Heat capacity we know Cp as T del S by del T P, or Cv as T del S by del T V. Now, any thermodynamic quantity, that is a very important quantity, that any thermodynamic quantity, any thermodynamic derivatives or changes can be expressed in terms of the above heat capacities. They are called in general all heat capacities. Because we can do that, we can express anything in terms of this thing. Since these are measurable, therefore, any other thermodynamic derivatives are measurable. So, although it might look very intimidating that we are told us to convert one to another, but believe me, that is the easiest part. The difficult part is actually measure them, quantify them, those are more difficult things. A simple change of one derivative to another derivative is not such a difficult thing once you understand that how to do that. So, therefore, this is a great advantage that any of the thermodynamic variables can be written in terms of these heat capacities that is mentioned above. Okay. So, why these compressibility factors are second derivative? Because as you can see that kappa t is obtained from derivative, taking derivative of v with respect to p. Now, v itself is obtained from taking the derivative of the fundamental equations, like mentioned above, that if you can go above, you see this v is obtained as del g by del p at a constant t. So, v itself is first derivative, and therefore, when you take the derivative of v, then it becomes a second derivative. Okay. So, now we are going to show you the usefulness of this Maxwell relations. Remember, during the calculation of Joule's coefficients, we encountered a term called du by dv, and at a constant t, and we did not have any expression of u from the equation of state, and therefore, we could not calculate that. But now, since we have since we know that how to get the equivalent derivatives from Maxwell relations, we can use that in order to calculate the quantities. For example, I will show you. So, we know that du is TdS minus PdV, but okay, that we already know. So, we are just writing it here, and then we are going to take the derivative. Okay, now we are going to take the derivative with respect to v. So, here is very important point, though I used to be myself get lot of confused, I used to get confused a lot earlier when I was learning myself, that how do I take the derivative of this particular thing. So, when I have written already the u in a differential form, taking derivative is nothing but dividing by another differential form. So, let us say I want to take a derivative with respect to v. So, what simply I am going to do is that divide both side by dv. Now, that gives us du by dv, and I want to do that at a constant temperature. So, now TdS by dv at a constant temperature minus Pdv by dv at a constant temperature. Now, that simply I am writing as del u by del v at a t, and since t is just a constant, it will come out del s by del v at a constant t minus dv dv will cancel, and I am going to get p. So, that is how you have to take derivative of this in these differentials. Now, we wanted to calculate this particular quantity du by dv in the Joule's expansion case. Now, how do I get that? Because we encountered this particular quantity del s by del v at a constant t, and that is difficult to measure. We do not know how to do that. So, you remember that del u by del v at a constant t was equal to minus C v n j, where n j is the Joule's coefficient, and isothermal version of the Joule's coefficient is du by dv at a t. And we said that for ideal gas it would be 0, and for a non-ideal gas like van der Waals gas or a real gas, it will be non-zero. So, what it means is that when you expand the volume at a constant internal energy u, and then the temperature is not going to change for an ideal gas, whether it will decrease for a real gas or for van der Waals gas. So, basically this is the coefficient that one has to calculate. So, but in order to calculate du by dv at a constant t, I have to get this particular quantity del s by del v at a constant t, and that is I do not know how to calculate that unless I talked about the Maxwell relation. And what is that Maxwell relation? We will do that again, we will not remember, we will just do SPTV, and we know that del s by del v at a constant t is nothing but del p by del t at a constant v, and both are going down. So, both are positive. So, I can write that as del p by del t at a constant v minus p. Now, that is very easy for us to calculate. So, for ideal gas, you know that P v equal to nRT. So, P equal to nRT by V. Now, let us take the derivative with respect to temperature at a constant volume. So, del V by del T at a constant V is, volume is constant, nR is a constant. So, nR by V del T by del T, which means nothing but nR by V. Now, I put that above in that particular equation 1, del u by del V at a constant T is now T into nr by V minus P, and you know nr by V is nothing but P. So, P minus P equal to 0. So, you can see that del U by del V at a constant T is 0. Since that is 0 and Cv is non-zero, Nj must be 0. So, Joule's coefficient is 0 for an ideal gas. However, that is not true for a real gas, and that we are going to show you. So, if you real gas is very difficult to do anyway. So, van der Waals gas is something that is intermediate between real gas and ideal gas, because van der Waals has that small volume V. So, you know that for an ideal gas P v equal to R T, P v bar means V by N. So, for a real gas we use some B factor for the size, and we write as this. However, in order to have attraction between the particles, we put another term as A by V square. So, that is our van der Waals gas equation of state. Now, if we want to calculate for this quantity del P by del T at a constant V, what do we get? We get R by V minus B, that is it, we get R by V minus B. So, del U by del V at a constant T is, you just want to see T del P by del T V, T del P by del T V minus P. Now, T R by V minus B minus P, and we know what P is, right? P is this quantity. So, R T by V minus B minus R T by V minus B plus A by V square, and this term cancels, giving me A by V square. So, as you can see that this V square of course is a positive quantity and A is also a positive quantity. So, therefore, this is greater than 0. Since this is greater than 0, you know that this is equal to minus C V N j. So, therefore, N j is minus 1 by C V A by V square, and C V is positive quantity, V square is positive quantity, A is positive quantity. So, N j is less than 0, and therefore, the Joule's coefficient is negative, indicating that for a free expansion the temperature of the system will decrease if there is an attraction between the particles, and that is indicated by A. If A would be 0, that means if there is no attraction between the particles, even if the particle has some size, the Joule's coefficient will not be affected, as you can see, because A is non-zero, because A is a positive quantity, because there is an attraction between the particles. When there is expansion, the particle has to overcome that attraction, and that will reduce the temperature of the system, and that you can see from after we get this Maxwell relation, it was possible for us to calculate that. So, you can do the similar thing with enthalpy. So, we know that dH is TdS plus VdP. So, I take derivative with respect to P on both sides. So, at a constant temperature. So, we get del S by del P at a constant temperature plus V. So, now I again use Maxwell relation S P T V. So, del S by del P at a constant T is nothing but del V by del T at a constant P plus V. So, that is my del H by del P at a constant T. Now, we know that P V equal to, oh yeah, because now you see that the arrows are going up and down. So, one will be minus, so del S by del P at a constant T is minus del V by del T at a constant P. So, now P V equal to nRT for an ideal gas. So, we need to calculate V. So, V is nRT by P. So, if I take a derivative with respect to T at a constant pressure, then it is nR by P, that is it, del T by del T at a constant pressure, which is nothing but nR by P. So, which means del H by del P at a constant T is equal to minus T into nR by P plus V. So, as you know that P v equal to nRT, right. So, P v equal to nRT. So, therefore, nRT by P is nothing but V. So, minus V plus V is equal to 0. So, del H by del P at a constant T is 0 for an ideal gas, and if you remember, that is nothing but the isothermal Joule-Thomson coefficient, or we call that as mu j T. So, that means at an isothermal condition, if you change the pressure, then enthalpy is not going to change, and therefore, the temperature is also not going to change, because that is related with temperature. So, now I am going to show you some special rule. So, you okay. So, before I do that, you can do the same thing for van der Waals gas as well, that I am not doing. So, special role of GTP. So, GTP is very special in the case that we can get everything from GTP. I am going to write down some of that here. So, if you have GTP, that means if you have free energy at a constant temperature and pressure, that means you get basically many quantities. For example, as you know, S already, it is del G by del T at a constant P, which means if you want to get your S, you vary temperature and calculate at every temperature, calculate the G, get the slope, and do the experiment in constant pressure, get the slope, and you get the value of entropy, and that is one of the way to get the entropy. So, in a lot of examples, for example, when you talk about solvation entropy, that means a protein or a biomolecule is in water. So, and that whether that changes the entropy or not, or an ion when you put sodium chloride in water, you know what happens, the sodium and chloride, they are attractive to each other, which means that they would like to be close together. But what happens is that when you put water, they get separated, because each of them gets solvated by water. So, first minima that was there, that is an energetic minima, because that was solvated, that was together by Coulombic attraction. But the later one, where the water molecules actually come and solvates both of them, that is called an entropic minima, because that solvent mediated minima that comes by after we put the water to solvate them. So, the thing is that if you want to calculate that, what you have to calculate is you have to vary the temperature and get the free energy of the process. Free energy calculation is easy, because it typically can be associated, as you can see later, for when you talk about equilibrium, binding constant and all, you will see that delta G is related to something like an equilibrium constant. So, once you know an equilibrium constant, then so once you know the number of unbound and bound species, so number of or mole of reactant and product, you get an equilibrium constant. Once you have an equilibrium constant, you get free energy. Once you have free energy, as you can see, then you actually can get to entropy by varying the temperature. So, that is why it is very important. People often forget how to get that, but this thermodynamic relations can tell you that already. How do you get a V then? So, you can get V by del G by del P at a constant T. You can get H as, you know, H minus T s is G. So, H is G plus T s, G you already know. So, only thing you need to know is S. So, it is G minus T into del G by del T P, and then you want to get, let us say, U is H plus H minus P v, U is H minus P v, because H is U plus P v. So, so how do you get H then? So, you get H as, okay, again H you already have from here. So, you can write G minus T del G by del T P. Now, you want P and V. So, you have V here, T, okay. So, that also you got, and then you want to get A is U minus T s, you already got from above, S already got from above, you can get that, and you can show that it can be written as G minus T del G by del T P minus P del G by del T del P T plus. So, this is u minus T s, and s is already given above. Yeah. So, it will be plus T del g by del t at a constant p. So, you can see that we can get pretty much everything from G. Cp, Cp as you know as T del S by del T at a constant pressure, which again is minus T, and S is again the derivative with respect to G, right. So, it is minus T del 2 G by del T 2 P. Now, you see why heat capacity is second derivative of the thermodynamic potential, and that can be shown for every other quantity as well.